Section 8.5 is over graphing rational functions. So we have a lot to talk about here when we are graphing, and then we'll get into actually graphing our different rationals. So to start, we need to look at the domain of a rational function. Because these are in fractions, we have some different things that we have to look at here. So as we know, domain tells us the x values that can be substituted into our equation. And the way that we have to use the domain for a rational function is we cannot have the denominator equal 0. So we're going to have some values that cannot be in the domain or are not part of the domain because it would cause the denominator to equal 0. So anytime you're asked about the domain and you have a fraction, we have to make sure that we are excluding those values that would make the denominator 0 because we cannot divide by 0. So these first three examples, what I have here is I look at what my denominator is. I have x minus 4 on this first one. I take that denominator, I set it not equal to 0. We solve and I get x cannot equal 4. So for number 1, my domain restrictions would be that x cannot equal 4. Similar to what we did when we were solving rational equations, we had to look at that denominator. Same thing here on number 2. This is already factored for us, so we just took both of those factors in the denominator, set each one not equal to 0, and we have our domain restrictions. And on number 3, we had to factor just the denominator. We only care about that denominator for our domain. I factored it. I got x plus 4 times x plus 5, set each of those factors not equal to 0, and solved, so we had 2 separate domain restrictions. All right, so just a little bit of review there. The main new thing when it comes to graphing a rational function is we are going to have what we call asymptotes. Okay, this is a boundary line that the graph will never touch. We'll go into some more details about what that actually looks like on our graph and some of our different rules when it comes to asymptotes. But that's our main thing. We have this kind of vertical line over here that the graph is avoiding. It will never touch that line. Okay. We have 2 different types of asymptotes. We have horizontal asymptotes and we have vertical asymptotes. So each different type of asymptote tells us different things about our graph. So if I look at some of our rules for horizontal asymptotes, because it is a horizontal line, it's going to be the equation y equals, because it's only going to cross our y-axis. Okay, think about when we would graph a horizontal line, it's only crossing that y-axis. So it's y equals that number. Okay, so that's why it's y equals. We are going to be looking at the different exponents of our rational function in order to determine our horizontal asymptote. So on the right side here, we have our different rules when it comes to the exponents. If the exponents are the same in the numerator and denominator, then we are going to look at the coefficients, the leading coefficient of each numerator and denominator, and divide those. Okay, so we'll get to some examples, but if we have the same exponent, numerator and denominator, we just divide the coefficients. Anytime that the exponents are larger in the denominator, then our horizontal asymptote is y equals 0. So it's going to go right along that x-axis line at y equals 0, horizontal asymptote there. And then if they are larger in the numerator, there is no horizontal asymptote. Okay, this page right here is going to be very helpful. These 3 rules to reference back to as we get to our graphing. Okay. All right, so some examples. If I look at number 1, I see that I have the same exponent, x squared and x squared. So same in the numerator and denominator. If it is the same, we divide the coefficients. Okay, so I see my coefficient is 6 over coefficient 3. We can simplify that to 2, which means the horizontal asymptote is y equals 2. If I jump over here to number 2, we see x squared over x to the third. That means the exponent is larger in the denominator. We go back up to our rules up above. If it is larger in the denominator, we have y is equal to 0 for our horizontal asymptote. Looking at number 3, similar to number 1, we have the same exponent in the numerator and denominator, x squared and x squared. We divide the coefficients. There's no numbers in front, so it's 1 over 1. It's going to equal 1, which means our horizontal asymptote is 1. And then number 4 here, I see x to the third and I see x, which would be like x to the first. The exponent is larger in the larger in the numerator. So if I go back to my rules, larger in the numerator means there is no horizontal asymptote. So I would just say there's none. Okay. So an example of each, if they're the same, you divide your coefficients. Larger in the denominator, you have horizontal asymptote of 0. Larger in the numerator, you do not have a horizontal asymptote. Okay. Now going to vertical asymptotes. This creates a few different things on our graph. So we have a little bit more to talk about than just our vertical asymptotes. But once we have all this information, we'll see how it all comes together on our graphs. So if we have factored everything in our function, and we have a factor that is only in the denominator, that means that whatever we get there, when we solve that factor, is going to be our vertical asymptote. Okay? So if I think back up to these that we had up above, if I had a factor that was only in the denominator, kind of like this x plus 1, if that was the only factor in the denominator and there wasn't a matching factor in the numerator, then that would create a vertical asymptote. Again, we'll put it all together in just a little bit, but it's looking for if we only have that factor in the denominator. If we have matching factors in the numerator and denominator, it creates what we call a hole in the graph. Okay? So it's just a spot on the graph that there is a hole, meaning the line does not continue through that point. Okay? So only in the denominator creates a vertical asymptote. In both the numerator and denominator creates a hole. And then if we only have a factor that's in the numerator, just in the numerator, nowhere else, then that is a root or an x-intercept. Okay? So we will put a lot of that together when we get to our graphs. But again, this table is going to be very helpful for you to reference back to as we get to our graphing. Okay, before I get to our graphs, yours should be on your paper here. But just a few things to throw in here to talk about our asymptotes so we can reference back to this information as well. So earlier I said an asymptote is a boundary line that your graph will never cross. Okay? The slight variation to that is the graph of the rational function will never cross a vertical asymptote. Okay? But it may or may not cross a horizontal asymptote. So, yes, it does not cross an asymptote, but it really just doesn't cross the vertical ones. It is okay if it crosses a horizontal asymptote. And we'll see what that looks like here in a little bit when we have our graphs. All right, there can only be one horizontal asymptote, and I threw in here or one oblique asymptote. We're not going to talk about those just yet, but we can never have both of those, but only one of those per graph. And an asymptote is not part of the graph of the function. So it helps us create the boundary line for the graph, but the asymptote itself is not part of the graph. All right, and then the second piece here, when we are going into graphing, we want to make sure we find the x-intercepts. We can plot those points. We can find the y-intercepts. If we plug in 0 for x, we can plot those points. Look for our vertical asymptotes. Set that denominator equal to 0. Find the horizontal asymptote, if there is one, using those 3 rules from earlier. And then we're going to have to plot a few extra points just to make sure we know where our graph is going. So that's what that last piece is, substitute in other x values to plot extra points so we have an accurate graph. So So far, lots of information that we are needing to use when we go to our graph. So reference back to the tables about horizontal and vertical and these different bullet points. Okay, let's jump into our first example. So I want to identify all my information and then we will go on to graphing it. So to determine our domain, we want to make sure that we factor our denominator and we find our domain restrictions. So I'm going to factor my denominator. I'm going to go through this part a little quickly just because we've been factoring quite a bit. Numbers that multiply to negative 30 but add to 1. So I know I'm going to want a positive 6 and a negative 5. When I set each one of those not equal to 0, I should get a negative 6 and a positive 5. So those are my domain restrictions. If I think about the factored form of my function, which is what we just did, we factored that denominator, I see that the only factors, x plus 6, x minus 5, they are only in the denominator. So I'm looking up here. If I have any factors that are only in the denominator, I have a vertical asymptote at that value. So I can go ahead and take that x and x plus 6 and x minus 5, and I know I will have vertical asymptotes at those two values. Okay, so they are domain restrictions, which means they're going to create vertical asymptotes there, so our graph will never cross them. Okay, our horizontal asymptote, this goes off of our exponents. I see an exponent 1 in the numerator, exponent 2 in the denominator. So we have the larger exponent in the denominator. If we go back to our rules, my larger exponent in the denominator means that the horizontal asymptote is 0. So I'm going to go to my line here and say y is equal to 0. Okay, for the wholes and roots, we have our rules right up here. I do not have any factors that are both in the numerator and denominator because I have my factor x, I have my factor x plus 6 and x minus 5. So no repeats there, which means we don't have any holes in the graph. And then if we look at the roots, this is where we're looking at just the numerator. I do have a factor that is only in the numerator. That is my factor x. So we would set that equal to 0. We solve. It is already solved. It is creating the ordered pair 0, 0. So I know that the root is 0, 0. Okay. What I like to do is either use like a highlighter or a colored pencil or something to draw in my asymptotes. So I know that my graph cannot touch those lines. And then I go through and graph from there. So I know vertical asymptotes at negative 6. So I got my highlighted line here. I know it will not cross at negative 6 and at positive 5. Okay. I have a horizontal asymptote at y equals 0. Okay. Remember, our graph can cross a horizontal asymptote. It just cannot cross a vertical asymptote. I also know that I have a root right here at 0, 0. So I'm going to plot my point 0, 0. And since there's no holes, we don't have to worry about that for this graph. So I know that it can be anywhere on this graph except for on those two vertical green lines. So I have chosen some points off to the side here to plug into my function. So I am choosing f of negative 8 to figure out where it falls on the graph, negative 3, positive 3, and positive 8. So I can get some points and figure out the shape of my graph. I just typed these into my calculator and I have some different values here. Don't have to be super precise on your decimals because we won't be able to graph that precisely, but it will be helpful to have a general idea. All right, so at negative 8, it is negative 0.3. At negative 3, it is 0.125, so positive. At 3, it is negative 0.2. And at 8, it is positive 0.2. Okay, so this looks like not a ton of information for us, but we have to remember that it will not cross our green lines here I have for the vertical asymptote. And we know that the line will approach that line. So I'm going to start by, I have that line that's going to approach it. I'm going to redo that just slightly here. So I actually have a curve. And since it goes below the line over here on the right, I know it's going to curve and just approach the other vertical asymptote. All right, on these edges, it is going to approach my horizontal asymptote and approach the vertical, and this one is up in the top right corner, so it's going to do the same thing. Okay, so not a perfect graph, but we see it's only crossing the horizontal asymptote there at the root, but then the other times it's just approaching the horizontal asymptote but not actually crossing it. Okay, take a little bit of work to get used to this, but you'll start to see these patterns, and once you have a few points plotted, you'll see where we can start to see what the graph will look like. All right, let's try out another one. First thing is we want to factor. So I'm going to look at my numerator. It looks like I could factor out a GCF of 2. Then it looks like I can factor what is inside the parentheses. Numbers that multiply to 6 but add to 5. I have 2 times 3 and 2 plus 3. So that is my numerator. And my denominator, we can factor right away. Multiplies to 2, adds to 3. We have 2 times 1 and 2 plus 1. Okay. So I have the factored form of my function right here that we're going to use to figure out the rest of our information. So I am, I am looking at the domain for domain restrictions. I take both of my denominator factors, x plus 2, set it not equal to 0, x plus 1, set it not equal to 0. And we have our domain restrictions of -2 and -1. I like to go right into my vertical asymptote because I will use similar information for the vertical asymptotes. I'm going to scroll back up here just so we can look at it. If we have a factor that is only in the denominator. So I am looking at my denominator. I see x plus 2 and x plus 1. Since I see another x plus 2 up in the numerator, the only factor that is only in the denominator is x plus 1. So my vertical asymptote is only at x equals -1. Okay, so since the x plus 2 is in both places, that is not part of our vertical asymptotes. All right, horizontal asymptotes. This is where we are looking at the exponents. So I look at my leading exponents here. They are the same. If we look back at our rules, the same exponents in the numerator and denominator will tell us that we need to divide the coefficients. So I'm going to take 2 over 1, which is 2. That tells me my horizontal asymptote is y equals 2. All right, and then looking back up here to the wholes and the roots, the last couple things we have. For the wholes, it's if we have some factors in the numerator and denominator, which we've already seen these. The x plus 2 shows up in the numerator and denominator. So if we were to solve that, we would have a whole at x equals -2. Okay, so making sure we're still solving, but because that's repeated in numerator and denominator. And our roots. This is where we are looking at whether the factor shows up only in the numerator. So I see that the factor that is only in the numerator is the x plus 3. When I go to solve that, I get x is equal to negative 3. So for the roots, I have negative 3, 0. All right. So I am going to start graphing. Again, I like to put in my vertical asymptotes first. In this case, it's just at that negative 1. I'm going to go ahead and put in my horizontal asymptote at y equals 2. When we go to graph the holes, I'm going to go ahead and put a temporary line at x equals negative 2. And the way I do that, I just put this dotted line so that I know when my graph approaches this, I will have to put a hole in its place. And we have our roots at the negative 3. And we are ready to plug in some points to graph. So I already have some of my values off to the side here. I plugged in negative 9 all the way to the left. I plugged in negative 1.5 because it's really close to my vertical asymptote line. And that'll tell me kind of the direction that the line should be going. I plugged in 0 for my y-intercept. And I plugged in 8 to go farther to the right of the graph so I know what's happening there. So at negative 9, it was 1.5. At negative 1.5, it was negative 6. At 0, it was positive 6. And at 8, it is 2.4. All right, so we know it's just going to be approaching our asymptotes. And it's crossing there. I'm going to skip that little line because it is the hole in the graph. And I'm going to go ahead and put a literal hole in the graph there. Okay. As we start to graph more of these, you will see the pattern. Here we have a curve in the top right and a curve in the bottom left. Okay. When we graphed earlier, we had that same curve in the top right, curve in the bottom left, but we also had that curve in the middle. So once you kind of start to see how these work, you'll see how your pattern kind of makes sense from each graph. Okay, one more graph together, and then we will look at kind of going in reverse for our last couple examples. All right, I'm going to factor everything first. So my factored function, I'm going to use what I know here to find my domain restrictions. Denominator not equal to 0. I have my two domain restrictions, not negative 6 and not negative 1. The factor x plus 6 is repeated in both the numerator and denominator. So my vertical asymptote is the factor that is only in the denominator. So I have x is equal to negative 1 for the vertical asymptote. That is because it's only in the denominator. For the horizontal asymptote, I have the same exponent in numerator and denominator. That tells me I'm going to divide my coefficients, which gives me y is equal to 1. For the holes, this is where we look at the matching factors in numerator and denominator. So that tells me that I will have a hole at x equals negative 6, because those factors are matching in the numerator and denominator. And for the roots, we're left with what is the only factor in the numerator, x minus 3 equals 0. We solve, and I have x is equal to 3. So I have 3, 0 for the root. Okay, so reference those rules every time. All right, my only vertical asymptote is at -1. My horizontal asymptote is at y equals 1. I have a root at 3, 0. And I have a hole at x equals -6. So I'm going to put that dotted line so that when I go to graph, I have that information there. Okay, again, I chose some points on the far edges of the graph, the -9 and the +9. I chose numbers close to my vertical asymptote, -2 and 0. So at -9, I had 1.5. At -2, I had 5. At 0, I have -3. And I didn't write my value down for 9, but it looks like when I graphed it, it was just below 1. I'll have to find that value there. So in some of our other graphs, we had a curve in the bottom left and a curve in the top right. In this case, it looks like we're going to have a curve in the top left and curve in the bottom right. So let's go ahead and follow our points. Again, I'm skipping that whole line so I can put in the hole in our graph. Not touching the vertical asymptote, not touching the horizontal asymptote. Again, it may or may not cross. In this case, it is not crossing the horizontal, but it can never cross the vertical. Okay, and we have it graphed. All right, our last two examples here. It says we are looking at the information given to us, and we need to write the graph, or write the function and sketch the graph. Okay, so with this information, we can figure out at least what factors are in the numerator and denominator, what are repeated in both parts, all of that stuff. So I'm going to go ahead and do f of x, and I'm going to set up my fraction bar. Okay, so we know that the vertical asymptote comes from the denominator. So if I have x is equal to 3, that means the factor would have had to be x equals, or x minus 3. So vertical asymptote comes from the denominator. The holes come from repeated factors in both the numerator and denominator. So if I have a hole at -1, that means I had x plus 1. So we're working backwards here. The roots come from a factor that is only in the numerator, and it was 4, 0. So that means I had x minus 4 because we had to factor. Or solve, I guess I should say. Okay. And the last piece here, the horizontal asymptote of 1 means we had the same exponent in the numerator and denominator, and we divided our coefficients. So sometimes it's helpful to go ahead and multiply these out to look at the standard form of our problem. So I have x squared, go through my multiplication real quick. So I can see I have same exponent, numerator and denominator, divide 1 by 1. That's how we're getting our horizontal asymptote of 1. Okay, so factored form and standard form could be helpful. I'm going to go ahead and fill in my graph with all the information that we have done. My vertical asymptote line. I have my horizontal asymptote line. I have my root at 4, and I have the hole at -1. Okay. Again, I went ahead and typed these in plugged them into the function to get some other values. I had 0.8 when I plugged in 9. I did 3.5, I got -1. At 2.5, I got 3. And at -8, I got 1.1. So I can go ahead and plot my other points. And again, we can kind of see our pattern here. We see it's going to be in the upper left and it's going to be in the bottom right. I fill my hole in there for that vertical line. And we graph the other side here. Okay. So this is where you're going to have to really get those rules down. Let's practice this one last time here, making sure we can figure out what our different rules tell us. Again, I like to start with the vertical asymptotes because those are kind of the same as our domain restrictions, because we know those are the lines that the graph cannot touch. So it's that line it will just approach. So my x equals 2 comes from x minus 2. And my x equals -1 comes from x plus 1. I see that I have a hole at x equals 3. When it is a hole, that means that it comes from the numerator and denominator. It has to be matching in both, so I should have an x minus 3 for both places there. And then the roots are values that only come from the numerator, and I have 2. So those two factors, 1 come from x minus 1, and 4 comes from x minus 4. Okay. So a little bit more going on here. I went ahead and multiplied this out just off to the side, just because it might be helpful to look at this. I got x to the third minus 8x squared plus 16x and minus 12. And in the denominator, x cubed minus 4x squared minus 5x plus 6. I won't typically give you ones that have x to the third power just because it's a little extra work to do, but this just kind of helps me see that I have the same exponents, which means I would have to divide the coefficients. 1 divided by 1 is how we have our horizontal asymptote of 1. So we can always check that work. You could also check it that we have 1, 2, 3 x's, 1, 2, 3 x's. Same exponents, divide, we would have horizontal asymptote of 1 as well. All right, and I'm ready to go ahead and put in my vertical asymptotes. X equals 2, x equals -1. Then I have horizontal asymptote at y equals 1. I have roots at 1 and 4. And I have a hole at x equals 3. Again, I just plugged these in. I just typed them all into the calculator at one time. All plugged in with -9 and then so on. This is kind of the more tedious part, but I'm doing a lot of points here at the beginning as I am kind of learning the pattern. But once you start to see where the lines are going to go, you'll be able to plug in fewer points. Okay, so -9, I have 1.5. -1.5, I have 7.9. At 0, I have -2. At 1.5, I have 1. And remember, it's okay for it to cross that horizontal asymptote. At 2.5, -1.3, and at 9, 0.6. All right, so I can see that there's something happening in the bottom right, in the top left. And then we'll do that middle piece. Let me fill in my lines so far. Remember, it's just approaching the vertical asymptote. It's not crossing. And then I have the hole here. All right, in the middle, it can cross that horizontal asymptote, but remember it is just approaching the vertical. So we see it's just kind of creating that slight little bend there in the middle. Okay. So the more points you have, the better it might be for getting that line accurate. But once you start to see the pattern, you can plot fewer of those extra points.